encountered in the last couple of years of building at Mapsense. So I'll give a little bit of a description of what our company is and then go through problems that we've encountered. And for each problem, I'll describe sort of hopefully a practical solution that we came up with to solve that problem. And then for each one of those problem solution pairs, I'll jump into kind of a quick demo that shows how we've actually implemented that solution in our product or in some back-end tool. And then hopefully after I go through these sort of problems and solutions, I'll jump into maybe a longer form demonstration of a couple data sets that we've been working on the last couple of years at Mapsense. And my goal is that at the end of this talk, you'll be able to leave the room with a couple of tricks or ideas that you can apply to your own research if you ever come across spatial data sets or the need to do any spatial analysis. So feel free to interrupt me or ask me questions if something's not clear. Yeah, and I'll get started. And before I do jump into those problems, I just want to kind of frame the world of mapping and the world of spatial analysis and what's going on today. And some of this might be familiar to some of you, but it's helpful to go over it. Kind of the biggest thing, and I think sort of one of the genesises of starting Mapsense, and I think a lot of even probably the Berkeley Institute of Data Science, is the fact that there's way, way more data being stored and collected today. So I call this internally, a tsunami of geodata. And this is just the fact that in the last few years, there's been not one order of magnitude, but several orders of magnitude increase in the amount of location data that companies are generating, streaming, storing, and collecting. And so this is coming from smartphones that are streaming location data, even non-smartphones that telecom companies can triangulate to locations. This is coming from connected cars, from Fitbits. This is coming from smart power grids that have sensors on them, like windmills and so on. There's companies now building very cheap satellites that can circle the world and make satellite imagery that's orthorectifiable. Drone companies are making satellite imagery, or not satellite imagery, drone imagery, that's also tied to location. And so there's many, many more sources of location data than there ever was before. An example that I often give is the company Uber, that you guys are all familiar with, is storing from every one of its drivers his or her location every 2 seconds. Some back of the envelope suggests that Uber's storing about 1 billion lat longs every single week. And you can contrast that with sort of the size of location data that people were playing with 5 years ago or 10 years ago. A big one that people would often talk about is the US Census, which was, if you think about it, at its finest discretization is about 300 million rows, updated every 10 years. So you can see that there really is like kind of a shift in the amount of location data that companies are collecting. And in addition to sort of the size of this data is streaming in. So you're getting data sets that are coming in real time. You're getting thousands of lat longs per second. And so you need tools to be playing with this sort of magnitude of location data. The second trend is the fact that, and this is kind of a little bit more focused on location or geo, is the fact that browsers are basically more powerful today than they ever were before. And that there's sort of been this shift or revolution in mapping, in making maps, and the fact that they can now be delivered to a browser and rendered on a browser. So I'll zoom out and do a little bit of a history lesson for you guys. Traditional web maps, like the MapQuests and the Google Maps when they were first introduced, were raster maps. So basically Google or MapQuest or whatever would take a bunch of location data in a database, render it into a bunch of images. These are like literally .png or JPEG images at every zoom level and at every lat long, and then just send those images to your browser. So they basically had pre-rendered the map. They chose the font size, they chose how the roads were gonna look, they chose when lakes would come in, and it was all very static. So they would render these big image tile sets and then send those over statically to your computer. Today, with like the advent of a browser that can actually do some computation on the front end, we can, instead of sending over pre-rendered map data, we can actually send over the raw map data. We can send the vector data, the actual XY coordinates of a polygon, send it over down to the client, and then make the client do the rendering of that map data. The advantages are many. So if you're sending over and delaying your rendering a little bit until it's right in front of the user, you can, there's a lot of things you get. One is interactivity, so you can actually touch the features. An image, it's just pixels, you can't actually select anything, but the computer knows this polygon is this polygon, so when the mouse clicks on it, select this polygon and bring up its metadata. You can also render the data, the feature as a function of its metadata. So let's say we're looking at buildings in San Francisco. Instead of rendering a map of buildings and then doing, and let's say we want to figure out, like, we want to color a map based on the price of buildings. We can send the price of the building associated with that feature and then have the client render the building as a function of its price. So you can do really data-driven mapping by sending the metadata of the feature along with the actual vector data and make the client do the rendering as you want it to. Then, let's say you send multiple pieces of metadata per each feature, you can, on client side, have the user change some toggle, re-render the buildings without hitting a server. If you wanted to do this in like kind of the traditional raster-based infrastructure, you'd have to pre-render a bunch of choropleths of buildings for every single data set you want. Maybe you want this to be real time, then you're really like kind of screwed because you can't render those things efficiently. So to make it very kind of obvious what I'm talking about, here is a traditional raster tile. You can see this is a .ping tile. I can't select it. This is an image. I can't change the fonts. The roads are predefined and so on. This is kind of what vector data would look like. Oh, looks like I broke that link, but here. So this is maybe a set of vector data that you would send down to the client and let the client render this data. So you can see the format of this data is in a format called topo.json, but you can send over any format of data, JSON, protobuf, or whatever. There's one other thing that you get with sending vector data down to the client is that you can choose how, like I mentioned this before, you can choose how you're going to render that vector data. An internal tool that we use at Mapsense. And this is a vector map that's being drawn on my browser. And one of the things you can do is change the style of this map really easily because the computer or my browser is figuring out how to render this map. So this was a little app that one of our product people built to actually color and choose a style for a map. And so you can get into here and let's change the roads and make them purple or whatever. You would not be able to do this with a traditional raster map. So hopefully it's becoming a little clearer to you the kinds of things you can do with a vector map. And throughout my talk, basically, I'm going to focus on these two trends. One is there are big sources of location data. Two is we have powerful browsers and we can start to do interesting things with these browsers that we couldn't do before. So in conjunction with massive real-time data sets. And that's sort of one of the, I would say that's a good description for the kinds of things we're focusing on in Mapsense. So I'm going to jump into our first problem. So the rest of this talk will be a set of problems and solutions and then a demos at the end. So the first problem is one that you've probably all heard of before. How long is the length of the coast? So this is a really famous paradox. The paradox is that you can't really measure the length of a coastline, even though it has some measurement. And if you measure, let's say we measure the length of Britain in miles, where each feature's biggest measurement must be in miles, you can make some measurement, and then you go down to centimeters, it's going to be longer, and then you go down to millimeters, it's going to be longer, and you can keep going forever. You'll never get a coastline. This is like studied by Mandelbrot and the whole theory of fractals that came out of this research. In our world, we want to render vector polygons in a browser. And one of the things that you might run into is if you send a full resolution file, that is the vector file, so XY coordinates for a very detailed polygon, you might be sending over a massive file. So let's say we're rendering the coastline of the world. We just want a map of the coasts. You're going to send over, and you have a full resolution coast file on your server. Even just download that to your client could take an hour, like the full resolution file. And so one of the tricks the trade, one of the tools that you would use is to simplify that data somehow such that you're not sending every single point in that big coastline file, you're only sending a subset of those points. So I'm going to just quickly show you an example of what happens when you don't do simplification. So this is an app that hit Hacker News a couple of weeks ago. And one of the problems that this author ran into was that he ran into so there are kind of techniques to handle this problem, and I'm going to go over one, which has a very, very hard name. It's called Visvalingham's approach, or Visvalingham's algorithm. And another algorithm, for those of you who probably know this space, is called Douglas-Peckerer. But Visvalingham's has some really nice properties. And the best property is that it's very, very intuitive, simple explanation. So I'm going to actually just explain it to you here with this image. Suppose that that top line is some really complicated coastline that you want to send down to your browser to draw. And so here there are 6 points, but imagine there are 600 billion points. Consider an algorithm where, excluding the endpoints, for every point you calculate the area of the triangle that's formed by it and its 2 adjacent points. So that's shown in the second image. And then every iteration of the algorithm basically remove the point whose triangle is smallest. So you can see that in step 1 we compute the triangles, and then in step 2 we remove 0.5 because its triangle is the smallest. Thinking about this intuitively, basically, we're removing the point that has the least perceptible difference between its adjacent points. And so this is a very, very intuitive algorithm. You can see we're just removing points that aren't that important. And it also has some nice properties. You can pre-compute this. You can apply the areas to points ahead of time. And this is really nice for basically performing this simplification like very, very quickly on a server, and then sending down simplified geometries down to the client. So here's a quick demo. This isn't a demo made by me. It's made by Mike Bostock of D3 fame. If I move my mouse all the way to the left, here's a fully, or this is, I guess, 65% of the points in the original Coastline file of the United States. And you can see the pixel area is basically the area of the smallest square triangle. So this is like 0.037 pixels. As I move my mouse over to the right, I'm going to simplify the United States, and I can keep simplifying. You can see now I've almost removed the San Francisco Bay Area. Manhattan has become like a block. And move it all the way to the right. There's the smallest triangle now is 100 square pixels. But I've reduced the size of this file to 0.80% of the original file size. Why is this nice? Because this is still totally perceptible. Everyone in this room, and I think everyone in the country, would be able to see this very quickly and see that this is the United States. So we obviously don't simplify this much in practice, but we can simplify maybe this much and still send down significantly reduced file sizes. And this is a really nice explanation. The coast of British Columbia, you can see that there are a lot of nooks and crannies in this data set. This actually represents, this little between Vancouver and Prince Rupert, this represents 10% of the Canadian coastline. If you could measure the length of a coastline. So I'm going to apply some simplification to this map, and you can see us reducing the amount of data we're sending. So if I make this number very large here, s equals 10, you can see that I've simplified the length of this coastline. I can make this really extreme, make it s equals 15. You can see very chunky. And then s equals, as I go down, s equals 7, s equals 4, and s equals 1, the full resolution coastline. And so this is one of the tricks that if you have kind of raw vector data on a server and you want to display it client-side, simplification of the vector data is really important. I'm going to go back to probably this and not go in presenter mode for my link. So hopefully this look okay. I love Google Docs. You can run into, so what I just explained works really nicely for lines and points. So you have roads or you have polygons, but what if you have big point data sets, like hundreds of millions of tweets or hundreds of millions of readings from mobile phones if you're a telecom company? You can run into a similar problem that you have too many points to display on a map. And so there are a lot of tricks to dealing with. You might want to turn this into a heat map, or you might want to cluster points into so that one point represents many points. But it's often really nice to actually maintain point data where you can click and every point still represents one feature. And so at Mapsense, we've actually taken sort of the analog of Visvalingham's algorithm and applied it also to points and are doing a similar density-based point simplification. So we basically look at regions, look at their relative density to their neighborhoods, and choose to simplify or thin out the data such that the geographic distribution of points is still maintained. This is my image for displaying that, and I'm actually going to show you a real data set where, and this link worked, where we're doing that sort of simplification. So here's a map. This is about 100 million tweets that I'm displaying on the map. But again, I'm not sending 100 million tweets down to the client. I'm sending a representative subset. And as I zoom in, I continue to do this point-based density simplification such that this, at every zoom level, you get the kind of best visual for that zoom level in that bounding box. So as I zoom into the US, you can see the major population centers in the Twitter map. And I'll zoom into Berkeley and we'll see what we can see. So the San Francisco Bay Area, you can see Sacramento and the city really light up. And the Bay Area view, we can see that looks like downtown SF, Giant Stadium has a cluster. Let's see what Berkeley looks like. Berkeley has a lot of tweets relative to its neighborhood. And we can zoom in very far and see this even like on a building by building level. So here's campus with a Twitter overlay or Twitter data set on top of it. So where are we? I think this is us, right? Yeah. Again, I'm sending over these points not as images or just sending over like an individual point. I'm sending the vector data associated with each one of these points so I can click on it and see what the text of this tweet. So I'm literally just counting the books on the shelf in the North Reading Room. The user description is, I procrastinate life. It's actually, so this brings up, this is a quick aside, but being able to start to map these really large data sets brings up issues around privacy, because Twitter probably doesn't think that people are mapping these data sets, but I can actually, a little bit more dangerous. You can see when Julie's tweeting at night and maybe figure out where she lives, and you can see what classes she goes to just based on the fact that this data has been mapped. But that's all public data. So I think that this brings up some points that I probably won't get too much into, but things that we're thinking about at Mapsense around basically user data and user privacy. I'm going to jump back into my talk, but this should hopefully have given you a demonstration of how you can apply similar ideas of simplification also to big point clouds.
So go ahead. About the exit that we see at the bottom, there is a behavior and time of the group of points that you're seeing at a time?
Yeah, I'm going to jump at the end of like going through these problems. I'll do like a couple of demos. But yeah, so this is actually just showing the distribution of the points that are in the current bounding box over time. So this is, it looks like I have, this data set is tweets over about 4 days, each of these humps. And so, and yeah.
When you said it's a sampling that you're doing on the server side as you zoom in and out.
Correct, yeah.
The simplification and sampling kind of blurred.
So yeah, I'm using some like poetic license there. It's not this, I'm not simplifying the data, I'm thinning it. But in some ways, I'm thinning a line to make it simpler, point data to make it simpler. But yeah, the goal is basically sending less data down to the client.
Well-crafted sampling.
Yeah.
Into some characteristics of
Correct. And the sampling that we perform here is not just like a random sample. We actually look at the geographic distribution. If you think about it, you can come up with some. It's not very complicated. Back to this one. Oh. So I've described sort of one problem solution. We have very, very detailed vectors on a server. We want to send them down to the client. How can we do it? We can simplify it, or we can thin it if it's points. The next problem, or kind of the next idea, actually governs a lot of what we do at Mapsense, and a lot of how we tackle visualization and analysis and so on. And that there's a very intuitive explanation, and then I can get into a little bit of math. But first, I'm going to do the very intuitive explanation, which I was discussing earlier, right before this talk. And the idea is, like a really intuitive idea is, since we're really focused on visualizing data, really large data sets, we can usually assume that we know where we're going to be looking because the consumption or what's kind of the backend is serving is a map. And the map can tell you its extent. And so when you can basically limit the data that you're looking for to the extent of the bounding box of the screen, you can make a lot of assumptions on a server that doesn't need to look globally, like to data points that are outside the extent of the screen. And so let's say I'm looking in San Francisco. If I have a very quick way to retrieve data that's in San Francisco, it's really nice for a mapping or a visualization because I don't need to actually ever pull data from disk that's not around San Francisco. Does that make sense? Okay, so that's sort of like the intuitive explanation. A more mathy explanation. We index all the geometries that we want to display in a big quadtree index. And so a quadtree index basically is an index that is a spatial index. And it divides up, it iteratively divides up like some space into 4 quadrants it's sort of a tree where every node has 4 children. And you can put features in the kind of node that most finely represents it. So you divide up a space into 4 quadrants. And if you think about how traditional image tile sets, back when I was talking about the Google Map Quests, they were serving images also in this form of kind of a big set of image tiles. It wasn't really a tile quadtree, but it was each image was described by its tile coordinates, which we've kind of taken and instead of calling these how am I going to say this? Instead of dividing up data into image tiles, we're indexing our features into a quadtree, and we actually call the keys tiles in a very similar way that Google Maps would tile a bunch of images. And so this image is kind of actually pretty enlightening. The way this works is at the very top, you can see one tile or one index in one key in our index. And it represents some very simplified data representing the entire world. So every zoom level here, which is kind of a level in our tree, which corresponds to a zoom level in the browser, represents the entire world. And as you get more nuanced features like tiny rivers and roads and so on, that you only index them in the tile that they should belong into. I feel like that was a little confusing, but hopefully with some hand waving you guys understood that. So what does this give us? Oh, and I mean, another thing that's really nice is that this is a really, this is an algorithm that's really easily distributed. The mapper basically iterates once through all the features and throws them into a tile. Like the key is a tile. And the reducer gets all the features that are in a key and then groups them into these tiles. And so it's really easy. I mean, this is distributed and runs on Hadoop. And so you can tile very, very quickly. So for those of you who understood, or for those of you who didn't understood, assume you can very, very quickly access location data for any zoom level on every lat long. Given that assumption, I'm going to go through some other problems that we were able to solve with it.
So when you say you calculate on a Hadoop kind of system, it says that you are split or sharding somehow between nodes. So the shard key is basically the
tile
level?
Zoom level, and it's a tile index, tile coordinate, like a z, x, y.
Yeah.
Yeah.
And
that's the key.
On that.
So this isn't for storing. This is just for the tiling operation.
So you're using pure MapReduce?
Yeah. So forget like different servers. Just the MapReduce, the keys are a tile coordinate, and the reducer is getting all the features in a tile coordinate. That make sense? And then, yeah, storing, we're doing some sharding, but most of our tiles, like tile sets, can be held on one machine or just replicated across machines. So I'm not talking about like geo-sharding here, which is something that we could talk about after this talk, which is super interesting stuff. Yeah. This is just on the tiling operation. Thinking about what I talked about before, simplification. Let's say you want to perform Visvalingam simplification. Given a really big input, like the entire coastline of the US, even, I gave you guys a nice trick to simplify that really big coastline, but that's a massive file that would be hard even to hold into memory. And so you don't need to perform Visvalingam simplification on that entire coastline. You only perform it on a subset of the coastline that represents the part of the world that you're looking at. And you can pull that part of the world into memory based on this index. So what does this data structure give us? A couple of things that I'm going to describe here. But one of the really nice things about how we're indexing our data is the fact that we can very quickly filter geographic data based on its metadata. And so I'm going to give you a demo of that here. Hopefully this link works. So here's San Francisco. Can anyone notice anything wrong with this map? Yeah, exactly. Yeah, the Golden Gate Bridge is missing. And I was able to do that by just putting a query in my URL. So you guys can read the query here. But what this query is saying is defining a group called group A, define it by some Boolean expression, where group A, where name equals Golden Gate Bridge. And I'm saying where group A is true, get rid of the bridge. If I'm going to put a false here, it's going to give you everything, just the bridge. And I'm able to basically query the underlying vector data very, very quickly because I have this index, this data structure on the back end. I'll show you another, maybe more practical example. Suppose I wanted the vector data just for buildings in San Francisco. I could perform a query where I, again, create a group. And this is a Boolean expression that I know is true for buildings. And I think it's like this. And so this is, again, I'm creating a group, defining a Boolean expression, and for everything that's not in that group, removing it. And so I'm very, very quickly able to do these sorts of filtering. On the traditional Postgres server with PostGIS installed, if you wanted to get the vector data for buildings in San Francisco, this query might take 30 seconds to run. I can put a minimum area filter on the end of this and get just the bigger buildings in San Francisco. And so we can do very, very fast operations on this geodata, sending down real vector data to the client. So it's not, again, this isn't image data. I have the name of these buildings and the elevation or whatever other metadata is associated with these buildings. I can go into more of that at the end when I give a couple more demos. Another thing that we have been doing at Mapsense, so this was a function of a real world problem that we ran into. We had a data set of all the crimes in San Francisco. And so this is coming from the city of San Francisco. It's a data set of about 15 million crimes over the last 10 years in San Francisco. So we got it from Datasets. The city actually publishes its own crime map, but it only publishes the last 2 weeks of crimes because it's such a large data set. So we dumped this entire data set, and we had a really nice point-based visualization of it. I could search it. It could search for different drug types or whatever, and I'll show you that at the end. But one of the things that when we showed this to some people in the city and some people, one of their feedbacks was, this is really nice that I can see clusters in this data set. But the police work not in these undefined regions. They work in police districts, or they work in census tracts, or they work in zip codes. And it's nice. Let me actually show you this. So here's that police data set. This is 15 million crimes in SF. You can see the date on the bottom. This is since 2004. Each one of these points represents a crime. So this is what happened. There was an arrest. Someone was booked in the Tenderloin for category other offenses on a Thursday. For each one of these points, I can also slice it by category over here. So here's a histogram of the crime categories. And let's say we're interested in the drunkenness category. So I'm going to just display crimes representing drunkenness. So these clusters were really interesting to a lot of people, But again, so going back to kind of why I brought up point and polygon, the police don't work in these kind of continuous areas. Okay, so look, it looks like North Beach, there are more crimes here, but is that in your police district or in my police district? And there's bureaucracy and how much money is alluded to those areas and so on. And so one of the things we wanted to do was to aggregate these crimes and be able to do these same sorts of filtering, but instead of drawing pure point clouds like this, show the police districts or census tracts with a count or the color associated with each crime. And so we did that, and I'll show it to you, and then I'll talk to you about how we did that. And so this is still like work in progress, so it's a little bit messier, but here's the same SFPD map with colored by census tract, where each census tract is colored by the count of crimes. And I can still filter on the underlying data. So I can do and where category equals drunkenness. I hope I spelled that right. Nope. Can anyone catch my typo? Two N. So this wasn't a pre-computed choropleth. This choropleth is computing on the fly, even on these really large data sets. And so going back to my slides, how are we able to do this point and polygon on really large data sets? So we've done this on hundreds of millions of points, and hundreds of millions, or not hundreds, probably tens of thousands of polygons. The traditional point and polygon algorithm is really simple. It's a ray casting algorithm. So you have a polygon and you have a point. Cast a ray in any direction out of that point. And you count the number of times it intersects the polygon. So you can see that in the image here. If it intersects an odd number of times, that point is in the polygon. And if it intersects an even number of times, that point is not in the polygon. It's really trivial to think about, and it's really intuitive. So you can imagine, the point over there, it's going to pass through 6 times. It's going to be even. If you cast a ray out and it never intersects because the ray was in some weird direction, that point is not inside the polygon. If it's inside, it'll pass through once. In every iteration with like self-intersections and so on, it always works. The proof of this is actually much more difficult than you think. It uses the Jordan curve theorem, like the fact that a closed curve intersects a space to 2 discrete spaces. But suppose you have 100 million points and you have a bunch of polygons and you want to perform this intersection. This would take a long time to run. But now think about the fact that we have the polygons are indexed in this quadtree. Can anyone imagine what your algorithm might be to make things faster?
Can you say the question again?
How can you speed up the point and polygon, given the fact that your polygons or your points are indexed in a way that you can quickly retrieve the features for a particular region in a quadtree?
You can pre-calculate the sign of each subtriangle and then show there's a trick path.
I don't know.
The first simplification is to use the bounding box of the polygon, and that you can exploit also your map quads because they have something to do with the bounding boxes. That can be very fast to eliminate most of the data points.
Yeah. So I think you give the answer that I was going to give, but basically, given a point, instead of intersecting against all the polygons in your data set, first figure out what tile it's in, because you can do that really, really quickly. And then only intersect it and do the ray casting algorithm on the features in that tile. And you can there's some tuning on how big your tile is, but basically that's the simple idea. And this lets us do really, really massive point and polygons on ingest of points that are coming in real time. We can still perform this point and polygon because we have our underlying polygonal data in a very, very fast data structure. So I'm going to give you another example of what we've done with this pointed polygon. And this is something that's really new also, that I think you're the first people to see this. We just got this map up last night. And we haven't explored all the possibilities of this. But what this is a map of is pings for mobile phones. So this is coming from one of our customers' datasets, who has a very popular very popular app, let's say. I don't want to give away too much. But we collected this dataset of about 3 million points, and we intersected every point, or we pointed polygon every point with the buildings in San Francisco. And what does this give us? It gives us a map of which buildings in San Francisco are popular, or which buildings have people in them, assuming who your users are, or who the users are of this app. There's still a lot of things, obviously, we want to do with like normalizing based on area. But this is some of the work that we're doing that's kind of a little bit more experimental. We're able to figure out like kind of real time which city or which part of the city is popular right now. So imagine, and just like I was able to filter on the SF crumbs on drunkenness and the choropleth would update, this is just a choropleth that works in the same way, and I can filter on time of day and show residential areas, and then I can do time of day equals business areas and business areas. What category of user is it, male or female, what are their ages, and so on. You can see like very interesting things just on, this is the entire data set, but here's, for example, the hospital or the UCSF and so on. And so this is sort of the combination of a lot of what I described at the very beginning of my talk. There are massive real-time ingest data sets, which is kind of what's behind this. And by doing nice spatial algorithms and sending vectors down to the client, you can make a map like this relatively easily. I'm going to give another kind of problem solution. And I'm going to have you guys make an assumption. And the assumption is, and this is a feature that we have kind of in our tile quadtrees is, excuse me. Suppose you have a polygon that sits in multiple tiles or multiple key values. You've actually chopped it. So you have a polygon, like a circle, and it has 2 tiles, and each tile just has like a half of that polygon. If you're just concentrated on visualization, that's okay. You can just kind of display half here and line them up, and it'll line up, and life will be good. But in many cases, it's helpful if your polygons that you've indexed in this tile index are actually mergeable. So you can grab those tiles, merge the polygons that are in that same polygon that's in associated tiles into one polygon. So this is the assumption that I'm going to ask you guys to make. Assume you have a tile index now where polygons are mergeable. And this is something that we've done. So our polygons are mergeable. And now I'm going to throw out a problem to you. Does everyone understand this idea of mergeable? Like the features are mergeable across tiles. So if you have a road that sits in many tiles, you can grab all those tiles, pull them into memory, and then reconstruct the entire road or the entire polygon or whatever. OK, so now we ran into a problem at Mapsense. This is the last problem I'll go over. Wow. Time. It's crazy. So the problem was this. Our base map is derived from OpenStreetMaps. And OpenStreetMaps does this kind of interesting but also kind of frustrating thing in that administrative boundaries like countries and states aren't clipped to the coast. So they actually include the nautical boundary of the world. So when you look at the, I'll show you, I think that that tile I got. Here, this doesn't show it. So you can see this is the border of a country, and this is the nautical border. So if I want to make administrative maps of the country boundaries, I'm going to get these weird nautical boundaries. This is really interesting for some tiny minority of people, but not for most people, and definitely not when you're trying to make a map of the world for use by people who don't know what that means. And so we were left with the problem that we wanted to intersect every single admin, every single country and state, with the Coastline file. Now the Coastline file is a massive file I kept alluding to over and over again. and we had to do many, many intersections. There are, states and countries together is like tens of thousands or even hundreds of thousands of polygons. I wanted to intersect each one with the entire coast. And so given our mergeable tiles, we're able to do this really, really nicely. And this is like, we didn't think, when we were tiling, we happened to spend a lot of extra time on making the tiles mergeable, and we really didn't realize the benefits of it because we were thought, okay, maybe we'll render it and we'll do client-side processing and we'll want the full feature geometries. We didn't really know what we were going to do with it. And this sort of came out as like a beautiful algorithm that we just jumped into later on when we need to solve the problem. And so the idea is this. Basically, let's say you want to clip the state of California to the coastlines. What you can do is you can take a bounding box, compute the tile cover of California, so the minimum number of tiles that cover the entire state, go to the coastline file, which has been tiled, grab those corresponding tiles, merge the coasts that sit in those tiles, and then do an intersection on a much smaller set of polygons. So now you're intersecting California only with the coastlines that it might intersect because they have the same tiles, and not with coastlines in Sri Lanka. Traditional, if you're just to run this masking on PostGIS, you're going to run it on the entire coastline files. It's going to take like 72 days to clip the entire world, which looks like some of you might have run into. And so this is just kind of another trick or problem solution pair that we've come into. This is the result of some testing. So we're really big believers in integration and unit tests at Mapsense. And this is on random data, where the light-colored orange is random coastline, and those little like darker colors are random states, and we're intersecting. You can see we're only intersecting the states with the coastline that it actually has the same tile cover. So I wanted to spend the last 5-10 minutes on giving you guys sort of like, now that I've shown you a bunch of problem solutions, give you guys sort of a culmination. What do we do now at Mapsense? These are some of the things we've run into or we've solved. And so I don't know how much time I'll have, but hopefully I'll go as fast as I can. Maybe I'll continue with this this data set right now. So this is a data set of crimes in San Francisco. This is those 15 million lat longs. I showed you how I can drill down on particular categories. So prostitution is one that has a particularly strong spatial trend. There are basically 2 clusters in the city where arrests for prostitution occur. And you can also see that my time filter on the bottom, these are really trending downward. So this was a problem, I mean, still is a problem today, but it's significantly less of a problem today. One of the things that's nice about how we index data at Mapsense is we also index for unstructured data or for text. And so associated with each one of these crimes is the actual text description that the officer wrote when he made the arrest. And we can search those text descriptions. And I showed this at an earlier speaking engagement where some of you were at. But it's interesting to search for different drug types to show where the distribution of those drugs are in San Francisco. So if you look for all arrests where the police report contained the word marijuana, this is going to be the resultant distribution. You can see that the tenderloin features a lot, but also this is the hate, where a lot of the hippies in San Francisco live, and this is the Mission, and there's North Beach. But if you were to look at the distribution of cocaine, for example, it's really tenderloin distributed along with a Mission, but not so much in the hate. A last and funny one is hallucinogens. Can anyone guess where this is going to be distributed? In Haight-Ashbury. I also wanted to show you a data set that we've started to work with recently. And this is a data set that's coming from the California Condor project. And so this is an organization, or several different kind of organizations that are working on protecting the condors. And so the data they get is basically coming from tags on the birds. So there are 120 condors in the wild. About 70 of them have GPS tags on them, and that are streaming their location data every single day. So we have the data. We've indexed the entire data set again. But I'm going to just zoom into a particular, let's say, week of data. And so this is 3 days worth of data. Each one of these points represents a reading from this data set. I'm going to color the points by the bird, so each individual bird. So this is bird number 374 and his patterns. And we also have kind of one of the most interesting things is to play with their speed. So was that bird flying around? Was he commuting, or was he nesting or eating or mating or whatever? So when you look at birds who are actually flying, so I'm going to drill down just on 10 to 20 kilometers per hour. And I'm just going to zoom into 1 day's worth of data here. So we can, if we just added some more functionality around temporal data, we can actually see this bird flying around. So these are the patterns for this guy, number 374. And so this is used by, sure, yeah.
Oh, yeah. So this is super impressive, but I just want to be clear and point out, this is a pound sign, not a question mark. So all of this is local JavaScript in Chrome. You're not calling the server at all.
So this is a really good point. We do a combination of server-side and client-side filtering. We try to abstract it from the user, from the UI, so that the user doesn't really need to think about what's going on. But yeah, of course, when I do this, that is completely client-side. Right. But when I drill, if you notice, I'm sort of doing this drill down functionality. That's hitting a server, and so that we've kind of made the UI so that the user doesn't know what's going on. But one of our tricks for doing really fast filtering is doing some of the filtering client side, and it's a really nice trick that you can do when you send vector data to the client. Yeah, good eye. One of the things that the field teams do, the Condor field teams, is also look at when the condors are not moving. So this usually represents where they're like sleeping at nighttime. And so you can see how this tool, which I'm able to over months or over a day or over a minute, just slice this I think this is probably tens of millions of lat longs, is a really nice tool for those teams to understand, okay, this is a tree that this bird likes to hang out with, or on this day he hung out here, but maybe we'll unlock time, just look at bird number 493, like we can understand his or her behavior over very long ranges of time. Yeah, and so I think I'll show you one more data set, which is the Twitter data set that I started playing with before. I think it looks better with dark color. And so this is a similar data set, except this is tweets and not condors or anything. And again, we're able to index the data or search the data on free text. And so one of the things that's really nice on the Twitter data set is to actually search the text of the tweets. First, I'm going to color the tweets by their language. One of the things that I haven't mentioned, but you might have noticed, is that all my charts are dynamic given my extent. So right now I have the whole world in my bounding box, and so this histogram is a good approximation of the distribution of languages in Twitter. But as I zoom around, so let's say I'm interested in European tweets, you can see that this histogram is updating. And so I can see now there's a lot more Spanish tweets or Turkish tweets are featured very heavily right now. And so all my charts are updating given my bounding box. And so as an example of this, I can type the word bonjour here. You can see France light up. You can also see, if you look at time on the bottom, people say bonjour at the beginning of the day. If you put in bonsoir, you can see time shift to the end of the day. And less people say it. One of the things that happened while we were collecting this data set was the Coachella Music Festival. And so I'm going to search for the word Coachella and show kind of what happened during that music festival. So Coachella, for those of you who don't know, is a really big, famous music festival that happens in Palm Springs. And so these are all tweets that mention the word Coachella somewhere in them. You can see my time filter at the bottom is showing very few tweets leading up to the event, and then a whole cluster of tweets at the end. And so if I'm going to play with time a little bit, this is, this broken? I'm going to refresh this to make the demo more interesting. Okay, so this is a couple days before Coachella. This is the day before, and then here's the music festival. And you can see a couple days before, the conversation around Coachella is located basically in Palm Springs in LA, like where that music festival happens. But as I move time over to the right, you can see the conversation becomes global. People in Europe, people in India, people in Manila are talking about Coachella. And if you click on a few of these, you can see that most people are lamenting not being at Coachella. Wish I was at Coachella. Why am I not being a gangsta hippie at Coachella? And this is, I didn't pre-can these. I would give a lung to be at Coachella. So this is really nice for sort of a global analysis, which languages are talking about Coachella and so on. But I can also even zoom into the Coachella Music Festival, which happens here in Palm Springs, and understand the same interaction, but at a very, very local level. So here is the fairgrounds where Coachella happens. Oh, zoomed in a little too far. You can see that a day before, or 2 days before, nobody's here. A day before, they open up the campground. This is where people can stay outside the music, like outside the concert. And then this is the concert. So this is day one, and then this is day two of the concert. You might be able to see sort of 4 clusters here. Those represent the stages at Coachella. Maybe, I wonder if this shows it. Yeah, so this is where Coachella happens. And we can even, again, this is the Twitter data set, which has a lot of implications. But we can start to look for, and this is some of what our customers do, look for influential people who are at this music festival. So influential people measured by a proxy of how many followers they have. So I'm going to size the circles by the number of followers that each user has on Twitter. I'm going to just drill down on people who have lots of followers. And I can even, again, given this data on Twitter, pull up their screen name. So color by screen name. Drill down on this person, Elon Music. This person is a famous DJ who's at Coachella. So for organizations or researchers who are interested in finding people or slicing big data sets, this is sort of some of our work. I know it's 2:05, and I just wanted to end my talk by saying that if you're a developer, we're about to release a whole set of self-serve developer tools online. This is a set of JavaScript APIs to do maps. This is a set of vector tiles to interact with those maps. You get the full featured OSM with all the metadata associated with the feature. So I can click on a park or a road and understand exactly what the data is in OSM on these roads. This is all the data you'll get. And then there are lots of different data sets we're releasing. So yeah, maybe we'll do questions. I don't know.
Yeah, thanks. We know some of you might have to go being 2 o'clock, but we have a whole half hour for those of you who have time to stay. We are trying to record this. Hopefully it turns up all right, but because we don't have mics to pass around, Erez will do his best to repeat your questions, but please.
Sure.
Your developer API, you're standardizing on TopoJSON to send to the client?
There'll be several formats. I think TopoJSON is the one we want people to use, but we're also going to release a protobuf, which will be faster. And I hope to release also a GeoJSON for simplicity. So I think the 3 we'll release will be Geo, Topo, and protobuf.
Thanks so much for that. That was so eye-opening and illuminating. And I get that you're a company and you work with clients. Which of the examples you showed us today are things that we can see outside of here? Particularly the Condor example, which I think would be great for wildlife classes here. People would really get a kick out of it.
So right now, yeah.
I mean, can we show that outside of here?
Yeah, we should talk, especially with open source data sets. I think we're actually going to release, in addition to these map data sets, some of those crime data sets and open source data sets for use by developers. Yeah, our company has been really focused and sort of heads down building, and then the couple of customers we have are big private corporations that don't want anyone to see their data. But our goal is to start releasing more self-serve, and we're starting that with this release. So I.
Stuff in particular was just so great. What we work with now is a few extensions in Arc.
I saw, so we talked to the Condor folks, and we interviewed them about their workflows, and basically they have an automated system that's sending around a KML every day to the field team that they open up in Google Earth that didn't have much filtering at all, and it was really laggy. So yeah, they were super excited. We're super excited. That project's awesome. Our goal is to make them happy enough that they take us to go see. Are there any other questions?
One word that didn't come up in any of these mapping descriptions is the word spherical. Because working in spherical coordinates, except in very small Cartesian spaces, and even computing areas dealing with Latin. I mean, it screws everything up. Point and polygon becomes a very tricky problem in practice to an almost impossible problem when dealing in spherical. Impossible to get right. You don't really have to answer this in any detail, but how much does that loom over all the things you're doing and complicate things?
I'm not the best person to answer this question. That's all I could say. I think
anything other than Mercator?
we do support and we will support other projections, but our goal is actually to serve lat long data and let you project it client side, which is one of the things that you can do when you're playing with vector data.
That's the coward's way out.
And I think the best person to answer this is our CTO, who deals with a lot of the topologizing and simplification and projection issues. I just can't speak to it.
I do have a question. I love the examples and started thinking here. Suppose now I don't want to do Condor. I want to have an NGO to track frogs, and I want to actually be the developer. So how do you make money? How this business will work?
Yeah, so this is still something we're figuring out as we release our developer tools. We actually have lots of other data sets. I think my favorite data set of all of our data set is the albatross data set. Again, these are a bunch of albatross in the Galapagos. Here, let me just show you this one really quick. I love this data set. Drill down on speed, size them by speed, color by ID. And you can watch these birds fly. And so these are birds that commute between the Galapagos and the mainland. And you can zoom in. I mean, this is about 1 million lat longs. You can zoom in pretty far here, see like particular. So you're not going to see it when I'm drilled down on speed equals this, but you can actually just see where they're nesting on this data set. So there's like a bunch that nest here. So this is a particular area where some of these birds are nesting. Anyway, so. Yeah, I know. I understand your question. Sorry?
I want to change that. I want to have a small business where anybody here would like to have a small business. They use these tools that are available. How much we are dependent on you? Of course, I mean, we're
yeah.
using your tools.
I think the way we're going to be, the way the developer tools will work is that you'll be able to push data. There'll be like it's almost like uploading it to Google Drive, but you'll upload it to Mapsense. We'll put these spatial indices on them. We can annotate data. So if you wanted the temperature added to every lat long or what administrative polygon it belongs to, we can annotate data and then expose it back to you in an API form or in a visual form, like kind of this tool. So that's going to be our developer product. So anyone can push data. There'll be nice endpoints for pushing and then querying back the data. And I think the way we'll probably do pricing based on like the amount of data that you send.
So it's most your prices between the amount of data that you need to store as opposed to the tools that you need to make available to show that top of open.
Yeah, I think all of everyone who ingests data in our infrastructure will have access to everything that I showed today. And so yeah, that's how we're thinking about it. You can upload your data to here and then use it the same way I'm using it internally.
Can you say a word about how you're using D3 in the map?
Sure. Yeah. That's a great question. Thank you. I mentioned that we're releasing a bunch of data to use. We're also releasing a D3-based mapping front end. So this is an alternative to Leaflet.js or any JavaScript mapping library like OpenLayers or whatever. And the idea is you get a D3 object that works across tiles. So it's very, very similar to, if you're familiar with D3, the kind of de facto graphics language on the browser today. But you also get to tile datasets. So you get a D3 selection. You can choose how you're going to color something. And then as you pan around and more data comes in, that selection will be applied to the latest data. So it's really, really nice if you're familiar with D3 and you want to do maps. Hopefully this will be really useful to you. You can do really cool things like delay the drawing like this. We have a whole bunch of tutorials. So like, for example, here's an elevation map in San Francisco. So this is 5-foot elevation lines. And I wanted to make an app where I could hover over that legend at the bottom and then select in the browser the lines that correspond. So this is something like this. The number of lines of code to do this is like extremely short. It's basically this. And all this is just putting the axis on the labels. But here I'm classing things by their elevation. I'm coloring things by their elevation. It's really, really nice framework. Yeah. So stay tuned. And if you're interested in any of that, please sign up for our developer list.